in our case, so they give you factorize the eta dependence you get for f and you get minus n plus n divided by n, and for j and n you get minus the other. Okay? So now you see that it's very easy to compute this. So you replace here n by 1. 1 is 0. And you take the absolute value, which is 1. So C equal x, y, so that x is less than 1 and y is less than 1 also. And for the other, for z, this is not n, I'm sorry, this is or. The or in mathematics includes the n. And d is in fact this and this may be checked together simply by adding both. You get x plus y less than 1. You see, because I invert this because they are 1 over in each case. Then I take the absolute value to this minus sign flip. And when I sum everything, I have 1. So that I get this impact. Okay, so x, y, so that x plus y is less than 1. So this is the convergent equation. If you take this plus this, well, intersection, you find that C, which is the region of convergence of set 2, may be drawn in the x, y plane as 1, 1, 0. Okay? So, from here, we have the whole square, and this gives a constraint x plus y less than 1. Okay, so you cannot take this formula to compute the value here if you keep only a few terms in the series, because you have to take them when you converge. But, of course, this is a trivial case. This is a very simple integral, so that the resummation may be performed. And this gives a very simple formula, in fact. I prime is nothing else but 1 over this plus y. Okay. I took this very simple example because it's speaking. And you see that if you take the resummation, this formula, there is no restriction in this part of x and y. You can take all the values you want. But in principle, keeping this series is not a rule to go where you want. Okay? And if you take only a few terms, also. Now you could have done exactly the same calculation for the other sets. Okay? It's a bit different, but I think you are a bit tired about these calculations. So there are a few interesting things that concern the other sets, which are not exactly the same as this one. But I think I will not speak about them. But something interesting is that at the end, what you find for instance, set yes. This set, I don't remember which one because I changed the numbers between here and here. You find another series of denomination which gives you, in fact, S2 equal to S2. That's S2, this is S3. For instance, S2. Okay, this is S3. If you do the same calculation with the other sets, this one, you find 1 over x sum n equals 0 plus infinity. Sum n equals 0 plus infinity. 1 over x to the minus sine power n. Y over x minus sine power n, and gamma 1 plus n plus n over n factorial n factorial. So you see, it looks like it's different. Indeed, if you compute the convergence region corresponding to this, you will find this region. Okay? But at the end, if you perform the restoration, you find nothing else than just it's the way of drawing x and y, okay, you understand? So, of course, you do the same answer once it is resolved. Okay, if you are able to do some analytic continuation, in this case, this is trivial, okay? And if you compute the set one, you find this region. Okay, so here you have no series representation of the integral which converge here. But the integral, you may compute it. It is converging the integral. It is not written anymore, but it is converging everywhere. So, to get the answer here, you have to perform the summation. Okay. So now we have seen all the tools necessary to compute the QED three-loop integral, and we did not do the calculation. Okay, because it's much more involved, and it will be boring now. But
so this is this main balance representation is the most powerful way to analytically compute, or do you think there are other maybe Greek ways?
There are,
other ways, I mean, which are more tricky and could give also good way to calculate analytically these higher loops?
My point of view is that yes, it's probably the best way to compute things now.
I mean, it was proposed when, more or less?
20 years ago.
Only 20 years ago.
Yes. Well, there were some papers before, but not known and not used as a mass way of doing calculation, massive way of doing calculation.
And it was used directly in connection with the G-2 calculation, or there were previous loop calculations involving many various representations?
No, there was previous.
There were previous, no, G-2 was just an application.
Yes. There was, for instance, this scalar things.
Okay, it's two
and things like this.
I see.
Diagrams that enter as master integrals.
I see.
A lot of calculations. But now I think it's one of the most powerful ways of computing things. Yes. I think I will just say a few words about the electric dipole moment, if you want.
Yes.
Just a few words. Okay. But here you know now the technique in a very simple case that you may apply to multiplicative integrals. Okay. So the EDM of leptons, of charge leptons. I'm not an expert, so I will not say much, but I told you that in the first course, when you write the matrix elements of the electromagnetic current between two charge leptons states, you have for minus charge leptons this expression. Well, this is the electromagnetic current. And this led to the anomaly, as we saw, and we computed a lot of things in this part of physics. But this also leads to a term which is minus F3 Q squared, sigma mu times gamma phi. And this term, this form factor, is related to the EDM, electric dipole moment of the charge leptons. This is a very interesting quantity. Okay, since you know that it's necessary for parity and time reversal to be variating for it to appear. So, if one can find a non-zero EDM for charge leptons, we will have a sign of CP violation, a new way of CP violation. Okay? In the standard model, the current value for D, this is D, dl. For the electron is 10 to the minus 38 centimeters. Okay, so this is very, very, very low. Very small, tiny contributions, which comes from 4 loop calculations. But 1 loop, 2 loop, 3 loops are 0. In fact, it doesn't exist before 3 loops in the standard model without massive net loops. And at 3 loops, if you do the calculation, you find 0. So you have to go at the 4 loop level to get this number, which explains why it's so small. Okay? If you add Majorana masses to the neutrinos, then you have contributions at the two-loop level. But anyway, the contributions massive. The contribution is, in one case, 10 to the minus 43. This is in a seesaw mechanism. And in a fine-tuned way, which implies a tricky cancellation between the masses of neutrinos, we can find at best 10 to the minus 33. Okay, which is anyway beyond the experimental possibilities today that we have. Well, I will give references for this. So, the standard model calculation, this for-loop calculation has been computed correctly. I mean, well, the three-loop was not correct. It was evaluated 1 year before the reference of the law, only by Plovich and Kospelov. In Soviet Journal of Nuclear Physics, 53, 68, 1991. Okay, see, this is the for-loop calculation. And this is by one of the same physicists, Kospelov, and others, in a paper which is Arkan Baum al Fisrev D17 Okay. Now, what is the experimental situation of the electron? I will not mention the others, the other chart papers. There is a very recent paper in Science that says that T is less than 8.7 times 10 to the minus 29. This is the Acme collaboration. This is 17th of January. Science. So, the number, and the page. Okay, so you see that we are still even in this very fine-tuned case, we are quite far still. And so, if you find in the experiment a value, a non-zero value, then it will be an indication of this beyond the standard model and this deviation contribution to this case. And I will finish by saying that there are hopes in the not so far future to find a non-zero value in some experiments. But when exactly, I don't know.
For some, and for the new, the
Yes.
EDM has not yet been measured experimentally.
Well, for the new one, this is something like
minus 90.
well, this is a number I found in some reference in 2010. So
Okay,
it's
2010.
2008.
Alright.
It's not so recent, but
I see.
and for the town,
Those proceedings you were using are 2010.
what?
Those proceedings I got from you, they are 2010.
Probably yes.
I see.
Yes, 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 yes. But this one is very recent.
Yeah, this is very recent.
So this is the last one we have. This is a very interesting quantity also, but no contributions in QED. I think I finished what I wanted to say. So I hope
Thank you so much indeed. It was it's a very good cooperation to our group, to the students here.
the last
Thank you
course
so much.
was a bit technical, but
Yeah.
it's important
Yeah.
to know when you come to things where they are valid. Otherwise, if you use wrong formulas, you can get numbers, but wrong numbers.
This is the first time they could get an explicit 2 and 3 loop calculation. We never did that here in the course. We never spoke about many environments, so it's very good for their knowledge.
These are simple 2-loop and 3-loop calculations, of course, because we have no time to do B and 1. But anyway, they are important and gives you some ideas, even if it's a bit tricky because not tricky, but simple because you put the one loop inside of 2 loop in an easy way that can be quite factorized. And, okay. Anyway, it's the 2-loop and 3-loop level. As a 3-loop case, we do not approach the general integral because it's very heavy. You have the tools to do it, and if you don't follow everything, you have the reference I cited. You're right. I wrote with my colleague and friend David Bernard.
Where is that now?
That's
in
in
Spain.
No, it's in Italy.
In Italy.
Yes.
I see. Where is the place?
It's in Naples.
I know.
It's dans Roseau.
Ah, we can also it's a good work there. I see. Yes. Okay, so thank you for the audience too. And,
Yes,
I hope someday you repeat these calculations. Someday in your life when you teach, you repeat this calculation.